Well, welcome everybody. Thanks for having me. It's my pleasure here to be here and yes, talk about event processing or stream processing. I call it pattern matching in sequential data. And in the title there's an and this and is more or less kind of dividing the two talks. So today I want to first give you an overview of this whole area, talk a bit about, well, the motivating scenarios, some applications, and then talk about some general query models that we would use in this area to conduct pattern matching or event stream processing. And we'll kind of, towards the end, more then think about or tell you a bit about what you could use to derive queries, to construct queries. Whereas then in the next talk, I think it is tomorrow, we'll talk about, or I'll talk about in much more detail on how to evaluate those queries efficiently. Because as I will already point out today, this evaluation is non-trivial. It comes with a lot of computational scalability challenges. And in the next talk, I'll then give an overview of some of the angles or some of the means that we can use to do query processing more efficiently. So since I also don't really have a good understanding of what kind of audience I'm talking to, please don't hesitate to give me a sign, to raise your arm, to stop me whenever you have a question, clarification, comment. I'm very fine to do this as interactive as you want. So I can later skip some slides or talk about some of the things in more detail, depending on your preferences. So it's all preference-based, as we learned. So I'm here to please you, yes, indeed. So just give me a sign, right? Just interrupt me. Don't be shy there. I rather spend, let's say, much more time on certain basic concepts than I'm fine maybe skipping some of the details of later stuff. Okay, Marlon already mentioned that I focus on different areas and I want to pick this up again. And actually, I now have 3 loves that I call it, not only 2. So, but the first one Marlon mentioned already, and I try to put all the research that we do in the group, databases and information systems, in Humboldt in Berlin, into this picture. So the first one is process mining and prediction, where in essence or what we look at is we have some real-world processes, some real-world phenomena. Right? This can be traditional business processes, like you have a travel expense process, or you need to renew your passport, something like that. Or it could also be healthcare processes, for instance, patient treatment processes. So those processes run in the real world. They are supported by infrastructure. And these infrastructures, these information systems, they produce data. While they support those processes, this data comes in the form of streams. So it may be continuously generated, or it may just be static data that resides in some database. And then we work on algorithms to analyze that data to eventually improve those processes. And those analysis algorithms, they then also run on certain infrastructures, of course. So this is one area, but not the area that I talked about today. The other one is, also mentioned by Marlon already, is data stream and event processing. So here the idea is that, this whole analysis is really done in an online fashion. So the basic idea, and I'll talk about the details later, but the basic idea of data and event stream processing is that you want to process data as it is more or less generated. So on the fly, without first storing it and then analyzing it retrospectively later, but you want to do this typically with low latency to take immediate countermeasures, for instance, based on some situation that you detected. So, again, we work on the analysis algorithms for stream processing, but then also on how to execute them most efficiently, in particular in a distributed environment. I'll talk to that about that in a second talk more. And the last one, this is actually the newest love. That's why was still missing in the enumeration here. I summarize it as exploratory data analysis. So here, this is a lot of interdisciplinary work that we do with different other disciplines, so in particular with astrophysics, with bioinformatics, where science is these days very much data-driven. So in astrophysics, we have a lot of colleagues that do nothing else than Python coding the whole day, right? People in bioinformatics that we work on, they also code all the time, not in Python, but more like in C and C++. But nevertheless, they are all crunching data. They are all crunching numbers. They all try to find patterns in certain data. They try to do this with very, very large data sets, particularly in astrophysics, but also in genomics and bioinformatics. And we try to help them to build the infrastructures, to build the environments to do their analysis. Right? Again, this is also something that I don't talk about today. I'll focus on the middle part. Okay, so data and event stream processing. Let me try to motivate that with some examples or some application areas, and let me start with one that I think you may be familiar with, or at least can relate to. I saw that here in Tartu as well. We have all kinds of sharing services. I haven't seen that many scooters, but I've seen a lot of bikes, shared bikes, right? So we have that, well, virtually everywhere these days. So you have those sharing opportunity or sharing services. You can rent a bike, you can rent a scooter, you can rent a car. And you may have not thought about it that much, but whenever you use an app to rent one of those, of course you produce data, right? And of course, this data is continuously produced. So we can think of that as a stream of data elements, where one of those elements may be, right, that a certain user reserved a certain bike at a certain position, right? Maybe for 15 minutes. I don't know how it works here in Tartu, but at least car sharing in Berlin use it, right? I can reserve a certain car for 15 minutes just to walk there, so that I can be sure that nobody, you know, sneaks in and grabs it before I get it. Another data element, another event, I will later call it, right, may indicate that a certain bike was unlocked, right, it was locked, or that some damage report was submitted. So all those data elements tell us that something has happened here, right, and they also carry additional information. So they would at least, those data elements, they would at least contain who was a user, who was a customer doing that, at what kind of location, which bike, maybe, you know, for what time did I reserve something, and so on and so forth. Right? So this is continuously generated data. Right? And now, typically, right, it's quite useful to analyze that data with low latency, so immediately, not only looking at the data 2 weeks ago, because you may, for instance, understand, right, that certain usage patterns are emerging. How do you understand that certain usage patterns of customers emerge? Well, you look for certain patterns in the data. So you may look, for instance, for a certain pattern of, well, a reserve event. So this is why we now have such a red shape here, right? Followed by some unlock event, and then followed by either one of those lock events or a damage submitted report event or data element. Right? So this is now a query that queries for a certain pattern, for a certain joint occurrences of data elements in such a stream of continuously generated data. Right? And in addition, right, we probably want to have some additional kind of constraints on the events that we would like to match. So for instance here, what is meant by this square bracket there is that all those events should relate to the same customer. Right? I don't want to interleave, I don't want to mix events that relate to different customers, or right, another example here would be that some of the events should also relate to the same location. I don't want to interleave, mix up events from different locations. Now this is just one example in urban transportation, right? But we have similar use cases, similar application scenarios also elsewhere. So let me very quickly introduce 2 more of those areas, but there are many more. One is cluster management, right? Think of a compute cluster with hundreds, if not thousands of nodes, right? You run all kinds of jobs. There's some cluster management, resource manager running there. You submit jobs to this cluster, right? There are all kinds of, again, status events that signal that certain things has happened, right? So for instance, if you submit jobs to a job queue, or jobs that should be run on the cluster, right? There are certain events that indicate that a certain job was scheduled, right? Maybe it was a certain priority, right? There's an event that a certain job terminated. There's maybe an event that indicates that a certain job failed execution, right? And sometimes those jobs are also preempted. They are evicted from execution simply because maybe there was some higher priority job scheduled to run on machines with a certain characteristics, right? Again, right, you may want to identify operational issues in such in running such a cluster. So you may look for certain patterns, right? And here such a pattern may be that you have a sequence, right, of a scheduling event for a certain job that is now followed by, this is why this shape is kind of dashed has a dashed outline, is followed by potential multiple of those scheduling events, right? So you may know a clinic closure operator, right? That simply collects kind of a couple of or a certain number of events, right? And then this is followed by an evict event, right? And apparently those scheduling events, right, that you collect here with such a query, they should all relate to the same machine, whereas the first one and the last one, so the evicted job, that should be events of the same job, right? Whereas those events in the middle, they should come from different, or could potentially be different jobs, right? So again, another query pattern. And last one here, this is actually a picture of some of the industry partners that we collaborate with in Berlin. It's kind of a company producing those robots that run in warehouses, that run in kind of to support production processes, right? So they move around and they are equipped with all kinds of sensors to operate rather autonomously in this production hall, right? And again, kind of we have a similar kind of setting, right? We have data that is continuously generated by each of those robots. Right, they have different sensors. I mean, I'm simplifying here a lot, but just to make the point, right? So some have camera sensors, some have LiDAR sensors, and then they may also generate certain events that, right, they detected certain obstacles with one of those sensors because, well, in such a hall, right, things are moving around, so they need to be adaptive here, and well, then, right. This would be accounted for if there's such an obstacle is detected, right? The other robots kind of react to that, but then at some point the obstacle is removed and then they can use a certain kind of gangway or hallway again. Right, so again, we would look for certain patterns. So for instance, right, either kind of there's an obstacle detected by camera sensor or LiDAR sensor, and then eventually this is cleared. So that would be now again such a similar pattern of data elements in such continuously generated data, right? Okay, so now I already used the term events quite a lot. So now you can ask yourself, okay, what is actually an event? Right, and if you look in the literature, of course, right, depending on the discipline, you find very different definitions of what people call an event. Interestingly, right, many of those different disciplines, even in philosophy, right, you would see that there's a temporal relation to that. Right? So what I consider here as an event mostly aligns with what originally comes from the publish-subscribe literature, so a middleware literature, which defines an event as a happening of interest, right, or also a significant state change. We'll get to that in a second. Now, if you think about that, this is a rather kind of generic term, right? Happening of interest, occurrence of interest, state change. And this is by design, in the sense that, yes, indeed, right, what we consider to be an event here is something that is very generic, and here is just an enumeration of, let's say, possible events that you can think of, right? It could be that you received an email, it's an event, right? It could be that, you know, a key is pressed on a keyboard. So if you have done some GUI programming already, you would probably have experienced kind of event handling mechanism, right? So because many of those GUI programming frameworks, they are inherently event-driven. Somebody clicked on something, somebody moved a pointer, and so on and so forth, right? So this is there we have event kind of orientation, right? In a warehouse, right, there may be an example of being low on a certain item, right? But you may even think of something as complex as hiring a new employee as an event, right? That is an event that changes a state from, well, University of Tartu hired a new employee, right? So probably now this is not the same granularity as, well, connecting a USB stick to a port. At least from my experience at Humboldt, this is not kind of the same time scale, right? However, the point is that, right, this generic notion of event kind of subsumes all of those things, and that's why I would argue, of course I'm biased here, but I would argue that event processing, this whole thinking event processing, is something that is very generic. It's general purpose technology that we can use in all kinds of application scenarios. Okay, now, so I said already, observable happening, some occurrence of interest, situation of interest, leads to a change of state. So there's some system that has it before the event and after the event, right? Before I press a keyboard and after I press the key on the keyboard. And well, there has been quite some debate in the community on whether an event has time or not. Right? I would here stick to the definition that events are instantaneous, so they don't have a duration. When you want to model duration, right, you can always model kind of some start and end event, right? But there are other people that strongly debate that. So I once was at a research symposium in Darkstuhl, and I spent actually 3 hours with a group of 15 people arguing just about the question whether an event has a duration or not. And people came from different communities, from AI, from databases, from more like the field of process management. They all had different thoughts on that, and in the end agreed to disagree. However, right, for the time being, or for this talk here, I'll think of that as something instantaneously. Also, I just want to mention here that in particular, if you look into the literature, actually terminology is a bit of a mess. In particular, when it comes to the distinction of, or the distinction between an event, what is the event, and what is a representation of an event. So sometimes this is called an event object, or event notification, or just notification. The point being that the event is something that happens, right? That doesn't travel, it's just happening, right? So you hired the employee, you press the keyboard key, right? But then there may be representations of that event, and those can travel, right? Those can travel to different systems. They can be actually also replicated. You may have multiple notifications of the same event, simply because, right, there may be multiple observers observing a certain event and then generating data about it. Okay. However, in the literature, you typically find that this is not so crystal sharp, this distinction, and often those terms are used interchangeably. Now, when we have those scenarios where we have events, like in this app where I book bikes or shared bikes, right? Then a common observation is that most events are not interesting, right? So maybe the actual booking event for such a shared bike is quite interesting because I want to invoice people, I want to bill people, right? But if you think about, for instance, all the kind of location information that you also have, right? I'm not sure about the bikes here, but at least the car-sharing cars in Berlin, they of course always have kind of tracked their GPS position. They would submit this, right? So most of those events are not interesting because in the end for the company, right, it may not be that interesting where all the cars exactly, which routes they go, right? Some things are interesting if they leave the country border maybe, but most of those events are not interesting. Also, we see in many of those applications that new events supersede old events, which simply means that typically the newer or the more recent events are more interesting than the very old events, right? So if I want to understand usage patterns of the bike sharing application, I typically are interested in the current usage patterns, not in those usage patterns 2 years ago, right? Or maybe 2 months ago. I mean, I can do a comparison, how it changed, then it becomes relevant again, right? But for operational management, typically the most recent data is most interesting. And in many of those, what also those scenarios have in common is that the ability to react to changing situation provides some inherent value, right? So that means that there is value in doing this data processing on the fly, in directly kind of analyzing the data and not only doing that retrospectively, right? And this leads to this whole field of complex event processing, where in the end, well, the input are some simple events that denote some, atomic maybe state change, whereas again, atomicity here is a kind of a very flexible term, as I've discussed initially, right? Think of key press versus hiring an employee, from which I then derive some complex event by, well, detecting a certain pattern, right? So that is the complex event, the patterns. This is actually what provides the value, what is interesting. So this now leads to this area of complex event processing, where in general, you could argue, well, what is the input? The input is streaming data that comes from information systems or from sensor network, from all kinds of sources, that is continuously produced, and that is now continuously processed by a complex event processing system that takes as input the event stream, or multiple event streams, and a set of event queries, so definitions of those patterns that should be detected. Some people call such a CEP system a database turned upside down. Why is it called a database turned upside down? Because when you think about a traditional database, you would argue, well, you have the data that is relatively static, right? And then you have a stream of queries that are actually submitted to a database system, right? If you think about the plain traditional relational database management system, the data, of course, the data can change, right? You can have update queries and inserts into your database, fine. But the data in large is relatively static or doesn't change that frequently, whereas if queries are something that is very dynamic, right? They are fired at the database system all the time and need to be answered, whereas here it's the other way around, right? Here the queries would be rather static. They are also called standing queries because you can think of those queries as being, well, once defined, once deployed, they are simply standing there while the data is streaming into the system, and then the queries, they do not change, but they are continuously evaluated all the time, whereas the data is changing at a very, very high rate. Right? Typically here, stream processing systems, right, typically talk about processing thousands, tens of thousands, hundreds of thousands, sometimes even millions of events per second. Right? So that's really the rate of the data that you want to process. Okay, now let me jump a bit more into those basic concepts here. So the event stream, right, just to summarize it here again, from the initial examples, if you try to abstract it, well, in the end, we have a set of data elements for which an order is induced, right? There are different models, whether the order is total, whether the order is only partial, whether that is induced by time or by position in some, sequence of generating the data, doesn't really matter, but typically there needs to be an order. If not, right, we can't really call it a stream. Then it's simply a set. So we have to have some notion of time, some notion of sequential ordering here. Again, maybe let me highlight also here that this is in practice something that is very tricky because it sounds simple. Yeah, I mean, you have timestamped data, right? So simply sort your elements by time and then you have a sequence of the data. Fine, in practice, right? The issue is that timestamps may have very different meanings, right? So you may have the time that actually signals that the event occurred, but maybe, right, this is not actually what is represented by the timestamp, but it's more like when the event was detected, which is not necessarily, right, when the event occurred. So if I reserve a bike, right, maybe the system, because my mobile is not connected, only receives kind of the information about my reservation a bit later. So the question is, which of those timestamps do you take, right? So in practice, it's maybe a bit tricky, but let's assume, right, we can order elements and we have a stream. Sometimes, right, we see also that there's some inherent partitioning. Well, that becomes later important in the next talk when we talk about distributed processing, because then some of the, evaluation may be pushed to event sources where they are generated. Also, sometimes, right, we see that those events are typed. So what I indicated here already with the colors on the slide and mentioned here in the examples in the beginning, right, that we may have elements that have a different meaning because one event here signals that I don't know, unlocked. This is the camera example, that I have an obstacle detected by camera or that the floor is clear to be used, right? There are different kinds of events. However, right, sometimes this is modeled explicitly by having elements of different types. Sometimes this is simply then pushed later into the evaluation of conditions over those payload data, what we call payload data here. The evaluation of all the data that is typically also assigned to those data elements. So think of those data elements, right, simply as a tuple. We have some schema, we have some attributes, and then we have attribute values. Okay. Now, if we want to define pattern over those event streams, what can we do? Well, we have event query languages. What do those event query languages look like? Well, they have a common set of core sets. So first, there may be, right, a set of type definitions. As I said, some of those languages do this. Others assume that this is already part of the stream definition. Right? Apart from that, we would now have certain operators that enable us, right, to specify a pattern over those types. Now, what are common operators? Common operators are sequences. Right? I want to have a sequence of certain types. I want to have a joint occurrence, so a conjunction of certain types. I want to have a sequence of types, but I don't know how many of those events I look for, right? I have a clean closure operator. I can also have negation, right? Testing for the absence of certain events. And So languages differ a bit when it comes to what kind of pattern operators they support. Here in the examples, you'll see that I mostly stick to sequential ordering, cleanly, and the joint occurrence, so the and or conjunctive operator. In addition, we may have correlation predicates that say, okay, certain elements that we want to match as part of a pattern, they should have certain attribute values, or they should agree on certain attribute values. And typically, we also have a temporal context. We have a time window because, well, the event stream, right? Conceptually, it's infinite, right? It doesn't end. It has a start, but it doesn't have an end. So we need to also bound, let's say, our evaluation interval when looking at the data and say, okay, I would like to, or I'm interested in identifying a certain pattern that occurs within a certain context. And typically, this context is time. Right? Again, you may specify this with absolute time or with kind of number of events that can happen in between. It doesn't matter, but typically you need to bound the context of the sequence that you look at. Right? So very simply, we may write this query as it is shown here. Right? And now you may think, okay, that looks a bit like SQL, and I come to the relation to SQL in a second. Right? It's just now a simple example here that would say, okay, I assume, right, that I have a stream that contains events of different types. Right? Those types may be C types, L types, and F types, and I'm now looking for a pattern of those events where I have a sequence of the joint occurrence of such a C event and an L event followed by an L event. Right? In addition, however, right, I want to only get patterns, or my pattern definition requires that all those events, right, refer to the same location, right? So the location attribute, abbreviated here as loc, the location attribute should be the same for all of those events. And they should appear within 1 minute. Right? So this is now one kind of way of defining such a query that you often find in research papers. I'll get to the link to practice in a second. Right, so this is essentially what I meant with kind of this illustration that I had on the initial slides. And you may notice here on the slide it says kind of that you have a nesting of those operators. Right? So if you have such a pattern definition, typically this is something that is tree structured so that you have a certain nesting of those operators. Here in this case, right, just a nesting of a sequence and a conjunction operator. However, in practice, right, that can get quite complex. Now, if I evaluate now such a query, then over the stream, right, what would I like to detect? Well, I would like to detect occurrences of events in that stream that satisfy exactly this pattern, right? So, for instance, right, in this example here, I'm looking for a sequence of such a, joint occurrence, so C and L event followed by an F event, right? I would find this maybe here, assuming that the time window is also satisfied, assuming that also those location predicates are satisfied, and I may find another one of those occurrences here, right? And you would see, okay, since I have this conjunction operator here, I don't care about the order of the C and L events, of the red and the yellow events. Okay. However, if you think about that in a bit more detail, you may notice that this is actually not as trivial as it looks like at the first glance. Because, in fact, right, if I now have multiple kind of events that qualify to be part of the pattern, I have to take certain assumptions on which of those events, if multiple of those events qualify to be part of a pattern, I should actually select into a pattern match. Right? And this is something that is typically then controlled or defined by so-called selection and consumption policy or reuse policies, right? That I very quickly just want to illustrate here. So if you have a kind of a sequence where it just checks for a sequence of an A event followed by a B event, and you have such a stream of events, now indicated with the respective types here, right? So the at the bottom, the green parts are now the individual events, so you would have an A event here, an B event, followed by another A event, and so on and so forth, right? Then, for instance, right, you may be interested only in patterns where the respective events follow up on each other directly, so you have strict contiguity, that is called, right? So there cannot be something happening in between, so I would have here only those, this red match here, right? But I wouldn't have another match for, let's say, for instance, of this A2 with this B2 here, because things are happening in between. Sometimes this is what I want, sometimes it's not what I want, right? Sometimes I want to be a bit more relaxed, right? Sometimes I want, for instance, I would like to have all kinds of A and B pairings, also if something happens in between. So for instance, I would also like to get this match here, this A event paired with this B event, even so there are other events happening in between, right? And maybe I even want to have this first A event paired with this last B event here, even so there are multiple qualifying A, B events in between. Right? This would be a very permissive selection policy. In the literature, it's called to skip till any match. So once you have identified a first candidate event, you are allowed to skip over any matches, any other event until you eventually find another event that matches. There are then others in between. Sometimes, you want to restrict the skipping a bit, so maybe you want to allow for things happening between events that you want to have as part of a pattern. But maybe, you want to avoid that. You want to generate, for instance, not this last match here, right? Because you would argue, no, wait. I have this A should not be paired with this B because there have been multiple A's in between already, right? So I should not be able to skip over those A and B events in between and thereby reduce the set of matches. Just to make the point here, so the point here is not about those particular policies, the point is about, okay, this matching semantics is actually, it's a bit more elaborated in practice because there are very subtle design definitions on what exactly you mean by the evaluation of even such a simple query as just a sequence of A and B event, right? And this goes on here, so you have also consumption policies, just very briefly. And so the question is, how often can I actually reuse a certain event, so a certain data element as part of matches, right? Maybe I want to make sure that for every event I only have potentially one pattern match, or maybe I can reuse this event as part of different pattern matches, right? Again, something that you may control, right? Again, same query here, same stream, and very different sets of matches. Maybe I'll leave it here at such stage. Again, takeaway here should be that that this whole matching semantics is something that is non-trivial to define. But regular expressions would be sufficient or not? Let me skip this question or postpone this question because I'll get to it in a second. Yes. I'll get back to it on the slide actually. So the question is now, what do people do in practice? Now I want to illustrate a bit what your options are to define such event queries in practice. And the first one is, something that relates to something that probably many of you know. So who has a basic understanding of SQL? Yes, I would think so. Who has heard about row pattern matching or match recognize in SQL? Yes, I thought so. Okay, not a lot. So this is something, the SQL standard is big. I think it's more than 3,000 pages these days. Since not the last revision, but the revision in 2016, however, there is a certain concept part of the standard that is called row pattern matching. And this enables us now to define queries as I have just introduced them. So, right, such kind of regex-like, regular expression-like pattern, and then some predicates and time windows. Now, how does that look like, right? This is a valid SQL query, right? Just looks huge, looks complicated, but it's actually quite reasonable once you got into it. So let me walk you through this. So this is a SQL query that starts with select star from R, which is something you all know. And then comes a keyword that is called match recognize, and this is exactly this row pattern matching operator that now defines a certain pattern. Now this has a number of keywords, right? And you will see that many of those keywords relate to concepts that I've just introduced. So for instance, the first line in this match recognize operator is now partition by. So we say that we only want to look for patterns into partitions of our data. By the way, let me say here that R here, select star from R, is a regular relation. So here we are not exactly talking about stream processing, right? But many of those database engines these days, right, they could also, well, not many, several of them can also work on streams. So they have kind of a concept of mapping streams to relations, because in the end I argued that a stream is nothing else than a set of tuples, right? They're ordered by timestamp. So once you have a temporal context, you can think of a stream always as a relation at a certain point in time. Okay. Now, we look for a pattern is within a certain partitioning of those tuples, right? Per se in SQL, if that is a plain relation, right, they are not ordered. So this is why in the second line here of the match recognize operator, we now specify this ordering. So we assume here that there's some attribute time, right? And we simply say, okay, this is what induces our order. So you see that here actually we can also define different orderings, because we could, right, maybe we have multiple timestamp attributes and we can select one of them to serve as an ordering criterion. We can also now define a time window, right? We can limit the duration. This is this clause here, right? Maybe to 1 hour. Now there is some policy here. After a match, we skip to next row. This relates to the selection and consumption policies that I just mentioned. So here we are telling or fine-tuning the semantics in the sense that, okay, when I now go through the ordered data and I found a certain match, I found a certain tuples that qualify, where shall I look for the next match, right? And this is saying that after match, it's quite readable in that sense. After match, you skip to the next row, so you only start looking at the first row that is part of the match. From the next row on, you look again for the next match. And now there's a pattern definition, right? And this here is indeed kind of think of that as a regular expression. So this simply means now that there's a sequence of some R variable, some U variable, and then some L and D variable that can occur in either order. So this is why there's this keyword permute here. So the permute is kind of the conjunction operator in match recognize. However, these are only type definitions, and now we need to go on and define what do we mean by those types. So what qualifies to be bound to such an R variable, right? And this comes now in this define clause. I would say, well, this is a variable for certain tuples, but for a tuple to qualify to be bound to the R variable, where it has to satisfy a certain condition, and in this case, the condition is always very simple here. Just the action attribute should be, well, this string that is mentioned here. So we see that here two things come together. On the one hand, and these are the, I would argue, most important clauses here in the match recognize operator. In the define clause, we in the end define an alphabet. So we define, you can think of that as tags that you can assign to certain tuples. So you have all your tuples in your table. And now for each tuple, you can evaluate, does it qualify as an R? Does it qualify as a U? Does it qualify as an L? Does it qualify as a D? In my case here, right, that those variables are mutually exclusive, so assuming that, right, they only have this one action attribute and has a certain value, a tuple cannot qualify as being an R and a U, right? But in general, this is not enforced, so you can have kind of right, a tuple can qualify to be bound to multiple of those variables. And then in the pattern definition, you in the end just have a regular expression over those type definitions, right? So we have two things here. So you have a regular expression, but you also have a definition of the alphabet over which this regular expression is defined. The last point then here, the measures clause is, well, you can think of that as an extended projection, as you may know it from SQL. So for each match, right, you may now execute additional kind of functions, you may transform the data, you construct the actual output that you want to have, right? You can also skip that, and then simply all the tuples that are matched become part of the output. Okay, so I hope you see that this is more or less, these are more or less the concepts that I just introduced as a basic concept of event queries, right? And the takeaway here is, yes, you can implement this actually in plain SQL, right? Plain SQL meaning standard SQL. However, right, I should also mention that not all companies or not all database systems, right, support this. But right, there is a kind of significant number of vendors, database system vendors that support it. So in Oracle relational database systems, for instance, you have support for it. Snowflake supports it. Trino, which is an open source kind of data processing framework, And in Azure Stream Analytics, you have the match recognize operator as well, right? Actually, I missed it here on the slides, but so in Microsoft SQL Server, you also got some support. I'm not sure on which kind of levels that is, but for instance, for some reason, IBM doesn't seem to care that much about it. So with that, now you can define this very declaratively, right? You have an SQL-like query and define it. However, I also want to mention that right, the landscape here is very heterogeneous. So in some systems, right, you have kind of the same concepts, but you define them in a very different way. Just two examples here. One is Apache Flink. So you probably heard about this one, many of you. It's kind of a big data processing system, framework for distributed data processing. It's tailored to stream processing in particular. Typically, mostly more like relational kind of stream processing, like sliding aggregates over streams. But it would also support with Flink CEP, for instance, it supports the definition of patterns, right? It's just that it doesn't provide such a declarative kind of nice query language. But you have to, right, define patterns here in a more like programmatic manner. So this is just here Java code taken from the Flink CEP website, where you see, okay, in the end we are defining a certain pattern here. It's actually a pattern of 3 events where we have a start event. A start event should satisfy a certain condition because the event ID should be 42. Right? We also have here a next event, this middle event. This should be of a particular type, so we can require this event to be of a certain particular type. Also, there's another data condition over it, and then there's a third event, right, that should also be followed here. Note that there is a next operator here followed by operator here, so that makes no difference whether we can skip over events in between or not. Next is immediately following, followed by maybe transitively followed or not eventually followed, right? And then we can evaluate such a pattern, right? Point here being, okay, not always do you have those nice declarative interfaces, but sometimes you have a very programmatic approach to specifying those queries. By the way, did I answer now your question on the regular expression? I wanted to have it here, right? So what we have in this pattern description here is mostly basic regular expressions. It's kind of sequencing, it's disjunction, it's conjunction, it's clean closure. Negation becomes now tricky, right? Because negation typically you want to have only in particular contexts. But yes, does that answer it, or is there more? Yes. But this pattern definition, I mean, in terms of basic operators, it would support like basic. You have also the cardinalities, right? You could specify something like you want to have multiple U events there, but at least 2, but maximum 5, something like that. Right? Yes, the syntax is not what you would typically have there, but yeah. Okay. Yeah, gotta change the standard. No, I would typically also write a plus there, but no, I don't have it here on the slides. Okay. Yeah, here we unfortunately have even more crude syntax. Anyway, just another example. So Esper is another CP engine. It's not really a database engine, but an engine built. It's also open source, built to do that. Just to give you another example, right? So unfortunately, languages are very heterogeneous, very diverse in that area. So right, you may now here see something that sounds very that you may remember from, let's say, basic SQL, select from, where, group by, having, right? So if you look here at the, what is it, also your left-hand side, right, this looks kind of reasonable, right? You may also see certain aggregations here in this having clause, for instance, but then, right, in the from clause, you actually have a pattern definition where you have such curly brackets here where we say for every occurrence of such a service order event that is followed by a product order event that has a certain correlation condition, so they must relate to the same customer ID, they must occur within 1 minute, and I only want to have those, right? The aggregation should be applied only to those that occur overall within 2 hours. Right, I then do all those aggregations. So I don't want to go into the syntax here too much, but again, the takeaway should be there are quite a number of languages out there. They differ a lot in terms of their syntax. Unfortunately, they also differ in very subtle aspects also in their semantics. Now, the question is, if we have one of those queries defined in one of those languages, how do we execute them? The most common way is actually based on automata, and there we are back to the regular expressions. It's just that typically right here, while you want to support those transition guards sometimes relate to data that was seen already, so you need to buffer some of the data. So it means that, so we have this query here, and it defines a certain pattern, right, as we have seen. So we can now generate a certain automaton, because in the end this is a regular expression, and we can now have an automaton that represents or that accepts all the sequences of elements, right, that satisfy this pattern. And in essence, this would just check for a sequence of an R followed by a U event, followed by L and D in either order. Right. What makes it a bit more interesting here is that, right, you have a lot of transition guards in those automata, because you need to check all those data conditions, like, you know, for the type of the events or a customer ID being of a certain value. You need to check the time window. And you see that you have in this automata here a lot of those self loops. So you have transitions from one state to itself, right, like, for instance, that one here. Right, and now the conditions at those self-loop transitions, they would encode actually those selection and consumption policies. Right, so the question whether you can skip over certain elements is exactly what is encoded in those transition guards here that are those self-loops. Right, and that is now something that we can evaluate. Right, and if we now evaluate it over a sequence of those data elements, right, then, well, after the first element, right, we keep now track of a partial run of this automaton, right? This partial run only selected this R event, because this is indeed what we were looking for here in the first state, right? If we then advance here, right, we now create two partial runs of this automaton that select or that concatenate this R1 event with this U1 and U2 event, right, where at the same time, right, assuming that we have a very permissive selection policy here, right, at the same time we would still keep this initial partial run of the automaton that only contains the R1, right, because this may be paired with maybe yet another U that comes later. If we now go on, right, and process the stream further, you see that we build up more and more partial matches, more and more partial runs of this automaton. Eventually, then with the occurrence of this D1, right, ending or getting into some of those accepting states, right? So here we would have generated the first two matches of this pattern, and you see that those two matches, right, they differ in the U event that was selected here, and they would be now part of the output. However, what you may also see already, or now, well, get a feeling for, that in particular under those permissive selection strategies, right, this blows up very quickly. So in the end, this is what makes the evaluation then very challenging. The result here may grow exponentially in the size of the input, right? So we may process a certain stream, a certain kind of number of elements, right? But the number of matches that we may generate may actually be larger, and it may, in the worst case, be even exponentially larger. Not for all kinds of queries, depends on the selection strategies and the operators and so on and so forth, but in general, that may be the case. Right? And even if the final output is not exponentially larger, the state that we need to maintain in terms of those partial runs, in terms of those partial matches, that may grow exponentially. Right? And with each of those arriving events, we need to check for all the partial runs whether we can now extend them with this newly received event or newly processed event. And this is something, this is why this exponential blow up or growth really hurts us, because it determines the evaluation or the evaluation complexity of the evaluation complexity of the runtime in the end. So most of those models are automata-based, right? There are some other examples that are then also tree-based, where you have work with trees of buffers that you then at regular intervals push data into those buffers, and then you have evaluation rounds where basically intuitively the idea is that you push the data into those leaf buffers, check certain conditions there, and then in certain evaluation rounds, you kind of push the data up the stream, always kind of pairing those events that satisfy the respective operator. I don't want to go here into detail, because actually many engines rely on on automata-based evaluation strategies. And in particular here, I found this once, and I was very happy with it, that I found this, because it was actually official Oracle user documentation, so it's a manual, that brings back kind of first semester computer science knowledge, right? So even as an DBA apparently working with Oracle, you should have an understanding of state machines. And why is that? Well, because in the end, if you run a match recognize query in Oracle, right? So in this particular example here, then you could see, right, that in the end the evaluation. So this is a query plan here that is generated for this query, and you would see here in the query plan here. Let me highlight it. Right, that for the match recognize operator, actually the evaluation, right, is based in this case on a DFA, not on an NFA, but right, so the query compiler, he would always try to generate a deterministic automaton, but it's not guaranteed that this, or it's not possible in all cases, so sometimes that may actually also generate an NFA here, and that may then, right, become computationally very, very challenging, very heavy. So this is why, even as a DBA, you need to understand state machines. Okay, right. So now let's see where we stand. Yes. So first part here, I wanted to give you some background on CEP in terms of motivating scenarios, in terms of the data models that we have in that area, and in terms of the query models. Now, what I want to talk about here in the summer school, that's the agenda for both parts, right, is now also, I want to highlight a bit how we get to those queries, because you can, well, have some nice techniques to create or to construct those queries. And then in the second part, I want to talk about the query, efficient query evaluation, because as I just mentioned, right, in general, query evaluation here in the general case has an exponential worst case time complexity. So there is a lot of, let's say, need to do this efficiently, and there are all kinds of different kind of perspectives on what you can leverage to make this query evaluation more efficient. And I want to give you an overview of that, and yeah, show you also some details of some of those techniques. Right, and then also in the second part, I also want to provide some outlook on open questions in this field. However, today I also want to give you some more details on automated query discovery, because this is something that I personally think is very useful in practice. Why is that? Well, because when talking about the motivating examples at the very beginning, right, I had this assumption that, well, users would know what relevant queries are, right? So you would know what are the kind of patterns that you look for in the stream. In some scenarios, that is very realistic, right? Because, well, I know how to detect a straggler, let's say, in a compute cluster, right? If kind of the execution time of a certain part of a job is on one machine, let's say at least five times as long as the average execution time of the same kind of different parts of the same job on other machines. This is my definition of a straggler. I can write this into a query. I can execute the query. Off I go. However, in many scenarios, right, this is not that trivial. I'm specifying kind of the right queries. On the one hand, right, there is only a partial understanding of what constitutes a situation of interest, right? So you may know, right, what maybe a straggler is, but you don't really understand, right, when it occurs, and you want to actually try to monitor and anticipate when a straggler will happen. And you may have some partial knowledge that relates to, for instance, a certain behavior that you see that a certain job is evicted, but you don't have a full picture. You don't really understand the kind of the interplay of the different jobs on your cluster that eventually lead to this job being evicted. Right? At the same time, in such scenarios, right, you would typically then also explore different query definitions. Right? You specify a query, you run it, you see, well, it doesn't really detect what I would like to detect, so you change it. And on top of that comes that many of those languages, as mentioned, they have actually quite complex query semantics. So those operators, those selection policies, once your query patterns become more complex than what I just had here on the slides, it's quite challenging to fully understand what you specify. Right? So that together makes query definition difficult. And well, actually now comes maybe the LLM point. So already 15 years ago, IBM worked a lot on natural language interfaces for CEP systems. At some point they stopped. I don't think that they ever came up with very, let's say, useful results. I mean, it was interesting and nice, but it didn't really solve the problem, right? If you're looking at the database field, there's an exponentially growing number of papers now on using LLMs to generate SQL. So for some reasons, the CEP niche was a bit overlooked so far, but I'm pretty sure that we'll soon see a lot of use LLMs to generate queries papers also in this area. However, what I want to talk about here is a bit different. Here the idea is a bit that in many scenarios, we would actually have historic data that was generated at some point, for which in retrospect we understood where in this data there were interesting situations. So for instance, right, we have cluster monitoring, we have the historic monitoring data, and we knew, well, here was a situation where we had a straggler or a job not completing or a job kind of doing weird things, right? Here we have kind of our, for instance, in finance data, right, you have streams of transactions and you know where certain fraud happened. You only know it retrospectively, and ideally you now want to have queries to anticipate, right, the fraud in the future. And here our idea was we worked on that, but also other people worked on that, to use historic data to support users in the definition of those queries and transform that a bit into a mining or discovery problem. In the sense that, well, we have historic event data, we have labels that indicate when something interesting happened, and now we can use those labels to split our event data into something, let's call traces here, and we take then those traces as kind of positive examples, right, as positive examples for some learning process to now discover queries that match exactly those traces, right? So visualized here, so if you have kind of the data, you would have some labels that tell you, okay, here was some of those, here were two situations of interest. I now split this into traces. How exactly I do this, right? It's a design choice, it's also an important one, right? Whether you do this kind of overlapping or not, let's ignore that for the time being here. Right, and now the idea is that, okay, if we have those traces, can I find event queries that now match all those traces? Right, and if you think about this, actually get to that in a second, sounds familiar to those of you who have heard about, let's say, many of those common data mining problems. I'll get to that in a second. So if we now want to discover event queries, there are actually a few things that we need to learn here. Right, we need to learn kind of a sequence of event variables. That's restricted to sequences here, but in general, we need to learn the pattern, right? We need to learn the type, the property abstractions, so those conditions that say, well, right, I'm only interested in events of jobs that run with priority larger than 5, right? And we need to identify correlation abstractions, so correlation predicates. So this is where the kind of, right, the correlation between, in the pattern, I want to have only those events of jobs that run on the same machine or that have been submitted by the same users. Those correlation predicates we also need to learn. And of course, a time window, right? So the idea is essentially that if in the one trace, again, just visualized here, right, I would find, okay, there's two scheduling events followed by a terminate event, right, where I also find that actually the first two events relate to the same machine, and the first and the third event relate to the same job. And I find the very same occurrences of two scheduling events followed by a terminate event with the same correlation predicates kind of being satisfied also in the second trace, right? I can now kind of come up with a query definition that checks exactly for this pattern. Disclaimer here, right, while this of course can be specified as a standard kind of discovery problem, right, given this historic data, given the labels, find all the queries. In practice, I would always argue that this is kind of a semi-automated approach that is only intended to support a user. It's not a kind of a push-button approach where I would say, okay, I generate the queries and then I'm done, right? So I would always assume that a user looks at those results, identifies whether that looks reasonable with some domain understanding, and not just plainly uses those results. Okay, right. Well, we want to have those, if we want to discover those queries, that should be correct. So they should match the traces, they should be minimal, right? So if I have kind of a query that matches all the traces that is very long, let's say, right? Any subquery of it will obviously also match all the traces and doesn't provide any additional value. So I only want to have the strictest queries that I can find, right? And ideally, well, there should be this complete. So if there exists a query, according to my query model, that matches all those traces, I want to find it, right? This is challenging in practice. Why? Because this is not only about finding the pattern, right? It's not only about regular expression mining, because we don't know the alphabet, because we also need to identify those property abstractions, right? Conditions only on a single event, as well as correlation abstractions, conditions that span multiple of those event variables. Right? And if we just explore this here for some real-world data set, right, this completely blows up the search space immediately, so we have an exponential blow-up, so we can't really do this in a naive manner. Right? I mentioned already this may sound familiar to quite a number of standard data mining problems, like frequent item set mining, frequent sequence mining, association rules mining, so you may have heard of those. However, right, my point here is really that this is different and this is more complex, right? Because with frequent sequence mining, we are only looking at frequent sequences, but we have a fixed alphabet, we have a fixed kind of set of types, right? Whereas here in our case, right, we don't have any types. We have multi-dimensional data, right? We have multivariate data, and we also need to discover those types. But of course, the discovery of types is always interlinked with the discovery of frequent sequences, or in general, frequent patterns. Right? And just to give you one brief overview over one of those approaches. One thing that we did, right, was to come up with a discovery approach here that first learned some, well, what we call event templates, then use a standard frequent sequence mining to learn ordering, and then construct those queries. Eventually also filtering the discovered queries, because you may want to show to the user only some representative queries for certain discovered queries. So let me very briefly give you the basic idea here. So the first thing that we do is to identify, well, promising, so to say, atomic conditions for data elements, for events that are promising in the sense that they would occur in all those traces, right? And we could consider those as templates that can be applied to all those different traces. So let me try to visualize that here. So if we have two traces, right, we'll have certain kind of atomic predicates that say, for instance, that the status attribute has a value schedule, right? And then we would find the events that satisfy this particular condition in all those traces, two traces here, and therefore we would consider it as a certain as a promising template. Right, maybe the same for this terminate here, maybe for the status, the status here equals to fail. We only find events that satisfy this condition in one of the traces, so if we want to identify queries that match all traces, both traces in that case, right, we don't want to consider it further. And lastly here, just to take another one, if the priority attribute equals 5, though maybe this is something that we consider again in two traces, and I just include that here to make the point that now for a certain event, of course, it can satisfy multiple conditions, as we'll see also on the next slide, right? So for instance, this event here in this trace, right, it satisfies this status equals schedule condition, but also this priority equals 5 condition. So in the next phase, we then interpret all the traces, right, according to those templates. So we in the end assign kind of those event templates to the elements in those sequences. And now this in the end means that we have assigned certain types to each element in those sequences, which means that we can now use standard frequent sequence mining techniques over those types, right? And that would generate us certain frequent sequences, for instance, like those, which again we consider to be now templates for query construction, because right, well, with those templates we go further, and in the third step now match those frequent sequences, or those templates that are derived from the frequent sequences, we map them back to each of those original traces to then reconstruct all the remaining correlation predicates that are satisfied. So again, I think it's best illustrated here with the example. So this is now one of those sequence templates that we derived by frequent sequence mining over those individual event templates. We would now evaluate this. We would identify that there are a couple of kind of matches for each of those sequence templates in the traces. And now we look for, or for mining or discovering now those correlation conditions, right? And would, for instance, see that if we have a condition that says, well, the first event has the same job ID as the last event, right? We find that this predicate holds true for at least one match in the one trace and at least one match in the other trace, then this is a candidate to take this condition into the query discovery, into the discovered query. Okay, well, we can actually show, right, that we have formal guarantees on correctness, on minimality. Completeness is challenging here when you have non-conjunctive queries, right? So why is this challenging? Well, in particular, if you have conditions, right, that are, for instance, inequalities. So you check, let's say, or you would like to discover a query that says, well, right, a certain event should have a priority larger than 3, right? Well, there's no guarantee that in the data you have exactly the data to determine this bound, for instance, of such an inequality, right? So that when, let's say, the proper query would be priority larger than 3, larger than 3, right? But in the data you would actually not have for all the traces the observation that is exactly on the bound at 3, but maybe only at 5 or something. So there is no, let's say, guarantee formally that we can give you. Okay, now, well, there are also evaluation results that, however, in the interest of time, let me skip over those and come to some other work in this area. So just now work here, recent work by our group. What we noticed is that, well, quite some people worked on this event query discovery. However, right, they came up with discovery algorithms, including myself 10 years ago, that were rather ad hoc. Right? So you have a problem and you come up with an algorithm, you evaluate it empirically, but this is all kind of, there are a lot of design choices, right? I mean, all the steps that I just explained with the event templates and the sequence templates that are then derived by frequent sequence mining. I mean, this is one way of doing it, right? But there are other ways of doing it. So we recently thought about, okay, how can we structure that a bit more systematically, right? So in general, we can think of that as a search problem because there is a search space of all the candidate queries. That is huge, right? Very huge. However, now the question is, how do we search through that space, right? And what we recently worked on and kind of, had some results is that we got an understanding of what are at least some of those basic design choices that you would do when searching through the space of candidate queries, and then think a bit more systematically about those design choices, which of those design choices make sense, which of those don't, and right, and well, then ideally also understanding which of those discovery algorithms that are derived from those design choices are useful in which particular context. All right, so in the end, well, what we came up with is such a framework defining dimensions for discovery algorithms, or for the definition of discovery algorithms, and then also providing some guidance on when to use which of those design choices. And I just want to sketch a bit how this works in general without going into the very details. So first, you can think of that search space of candidate queries that you have for a given set of traces as something that you may explore top-down or bottom-up. So we have a search space, visualized here, and the question is, do we search it top-down or bottom-up? Now you're asking, okay, wait a sec, what does that mean? So the idea here being that you can think of it in the following way. If I start, in my terminology here, this is top-down. If I start top-down with a search, then I start with a query that is very, very, very specific. So I have a number of traces, and I want to now find a query that matches all those traces. Now I'll take the shortest of those traces, and now I build a query that essentially encodes this trace. So this query contains event variables for each element in the shortest of my traces, and it contains conditions that encode all the attribute values of this particular query trace. Right? So then I have a query that probably matches exactly this one trace, but not the others ones. And then I try to relax this very strict query stepwise until I find a query that matches all the traces. On the contrary, I can also go bottom up, and I start essentially with an empty query, and I start making this query more and more stricter or more restrictive until, right, of all those queries, simple queries will then probably match all the traces, but then I go up and I make it stricter and stricter until, right, I hit the bound that is visualized here, where making it only a bit stricter will break the property that it matches all the traces. We try to illustrate that here. So, right, let's assume that our shortest trace only has maybe 2 elements, just for the sake of simplicity here. Right, then if I start top down, I would start maybe with this query here that essentially encodes this short trace entirely. So it would check for a sequence of 2 events, whereas I now spell out in this condition here all the attribute values of all the attributes of those 2 events in this trace. Right? As I said, most likely this query will then only match this one trace, but not the other ones. So I then kind of relax it stepwise, for instance, by dropping one of those conditions. Right? So I get from this query here to that query by simply here, right, dropping this one condition, leaving everything aside. Maybe that was already sufficient so that this query now not only matches this one trace from which I constructed it, but also all the other traces. Probably not, right? But this is the idea of top-down. On the contrary, as I said, right, I could also start with the empty query that matches everything, and then stepwise, right, kind of enumerate all kind of potential queries that are include now stepwise more and more assumptions on the events in the traces, right? So first one, I may just specify, okay, all the traces contain an event, right, for which the first attribute has this value that is given here, right? Maybe this now matches all the traces, but maybe a stricter query would also match all the traces, so I cannot stop here, but I want to get now stepwise, make this query more and more restrictive until I hit this bound where making it stricter, right, will break the property that it matches all the traces. So I hope that I now have at least an intuitive understanding of what I mean with a search space and how you can search through it, top down or bottom up. Right? Since we now have a search space that we search through, right, we can also argue whether we want to do this breadth first or depth first. Right? Kind of also a reasonable kind of design choice to do here. We can think about whether we want to separate in the search, whether we want to separate atomic and correlation predicates, or whether we always want to consider them in a unified manner. So what I mean by that is, and let's look at the upper 2 queries here. Right? This would be a query here that has only atomic predicates in the sense that all those conditions here, right, they relate to only one of those event variables. Right? So this red condition here relates to the first one event variable. This condition here relates to the second one. Right? Whereas this query here on the other side, right, this defines a correlation predicate, so that is a predicate that relates to both event variables. And now the question is, should I separate, right, the discovery of queries with those 2 types of predicates first? So I first only want to have the queries that are frequent and, right, minimal, that contain only atomic predicates and only correlation predicates, and then I merge them. Or do I want to consider every combination already right from the start, right? Considering every combination would mean that here the lower query would also be immediately be considered in the search, right? It's kind of a design choice. We may take either way here. And lastly, right, I can also have the same game, play the same game with the different attributes. So I can, let's say, do the discovery only for a single attribute of all the elements first. or for all the attributes in isolation, and then once I have the frequent or those queries that match all the traces per single attribute, I merge them again, or I can immediately do a unified construction considering all the attributes, right? So this now, right, leads to a certain space. So we have those 4 dimensions. However, right, there are quite some arguments that not every combination of those design choices makes a lot of sense. So for instance, so far we only looked at bottom-up approaches because typically the real-world data that we have is just that if you look at the search space, right, our queries are typically more towards, let's say, the lower end than to the upper end because the size of the traces that we have is typically much larger than the queries, for instance, in terms of the length, right? So there are some arguments why not all combinations make sense, right? But we identified, right, quite a number of reasonable combination of those design choices and then came up with those, let's say, 4 discovery algorithms that come from this more like systematic approach of thinking about query discovery and, well, also come with certain correctness guarantees here. Again, right, we'll also evaluated that, but here, oops, let me also jump a bit further over that, because, yes, because instead of, let's say, experimental results, let me quickly talk about some of the additional things that are useful now on top of that. So, right, in practice, again, when you use this now, this nice, works to some extent. However, in practice, what you would notice is that quite some interesting patterns you would not identify because real-world data is noisy. So this is why, right, typically, and with real-world data, you don't want to have queries that match all the traces, or that generalize over all the kind of observations that you had in the past, but that generalize over many, or maybe the majority, right? Maybe 90% of those observations. So you typically, in practice, would like to also have some support threshold here to factor in so that you have all the queries that match, let's say, at least 90% of the traces, right? And however, that is also something that is rather easy to integrate in practice, right? That increases runtime quite a lot. Oh, and something that I did not mention before, because I skipped the slide, but let me still mention it here. Right? All those discovery algorithms that I just motivated, right, combining those different design choices, they have, actually from a formal perspective, they have all the same worst case complexity. Right? So this is not a matter now of, in practice, of using one of them because it will always be better than the other one, but in practice it's about understanding what the actual runtime, how the actual runtime is influenced by properties of the data set, because, well, from a theoretical point of view, right, they are all the same. Good, and that still, right, becomes even, also holds once we introduce kind of support thresholds to play around with support. Even so, in practice, then the actual runtime that we would observe becomes even more challenging. Right? Also, something that is interesting from a practical point of view is thinking about incremental discovery, because, right, again, in a practical environment, you would like to, well, work with those discovered queries. So we see this as a tool to help users in the query definition. Right, so you look at discovered queries, you see, okay, this is not really what I was looking for. I see that there's a certain overfitting, which is probably due to some, bias in the data that I, as a user, understand that, but that was kind of not, obviously not inferable from the data alone. Right, so you play around with such discovery mechanisms, which means that you would also frequently now change the setting, meaning, well, changing the support value, right, or you may even have concept drift in the data so that, well, the database, so the set of traces that you consider as input for the discovery also changes, right? And again, this is something where a naive exploration, let's say, would be not so valuable. So this is why you want to do this in an incremental manner, and ideally, right, you have discovered certain queries and now you want to, well, be a bit more relaxed with your support threshold, and then you don't want to start immediately, recomputing everything from scratch, because everything that we do here is, from a computational point of view, it's a nightmare. Right, so you want to do this in an incremental manner. But these are, well, got some initial results on that, but this is also a lot of ongoing work. Okay, so let me conclude here so that we have also some time for questions. Let me skip over that one. So what I hope that I could demonstrate or show you is that, well, complex event processing, this pattern matching in temporal data and sequential data, is it's an interesting, useful paradigm, right, to detect certain situations whenever we have data that is ordered and whenever there's value, typically, of reacting to the occurrence of those situations. Right? And, well, if we want to do this kind of pattern detection or event processing, right, then we have a lot of tools around. So there's a bunch of query languages that are partly very expressive, right? And that enable us to specify patterns in a rather elaborated manner. And this is, on the one hand, good, because, well, we have an expressive query language, or a lot of expressive query languages out there. On the other hand, it's also kind of bad, or at least a challenge, in the sense, right, that in practice it's typically not that easy in many scenarios to define the exact kind of query semantics that one is interested in. That's why I think, at least, it's kind of also useful to think about tools to help users in the specification of those event queries, and this automated query discovery would be one of those, let's say, tools in the toolbox to help users in doing so. And with that, well, I close it for today. Thank you, and I'm open for questions. And of course, I also want to acknowledge that, well, I stand here and talk, but there were a lot of people involved here, in particular this work on query discovery. The last part that I mentioned, that was Rebecca, that's her, whoops, so yeah, well, in the back. That was her PhD work, actually. She is just about to submit, so yes. But here now, thank you, now I'm open for questions. Thanks.